Welcome to Lecture 4. In this lecture I'm going to introduce and define the notion of sequence. The informal definition of the sequence is that a sequence is a list. It can be a sequence of real numbers, sets, functions, or anything. By list we mean that there is a first element, second element, third element, and so on, continuing in an order forever. It is important to remember that in mathematics, finite list is not called a sequence. A sequence must continue without interruption. To formally define a sequence, the key role plays natural numbers. What we do in every item in the sequence, we label its position by saying first item is a 1, second 2, and so on. That is what we are doing. Is suppose we have list of items A1, A2, and so on. We are labeling it by saying this is 1, this is 2, this and so on. And what we are doing, we are defining a function which takes these natural numbers and give us back the set. So the sequence is a function which takes the natural numbers and gives us a list. Formally, a sequence of real numbers is a function defined by following way. So the domain is natural numbers and codomain, then the range is R or whatever set is in interest. So we can write the sequence as F1, F2, Fn, and so on. The F1, F2, and Fn called the terms. Let's now give a couple of famous examples of the sequences. Mostly we will concentrate on progression. So the first example is a arithmetic progression. In this case we have a sequence where each term, to get each term we add d to the previous term. And in this way we can define our function as, we can say fn is equal xn. We define it this way, c plus n minus 1d. The same way, the geometric progression is defined as multiplying each previous term by r. And in this case, the sequence can be defined as function which is equal c times r n minus 1. A sequence whose terms are following is denoted by x1, x2, or we can write the sequence in the following way. Therefore, let's say, for example, the sequence 1, 1/2, 1/4 can be represented as following way. Now what I will do, I will define very important notion which called the countability. Let's define it. If we have a set S which has real numbers, it said it to be countable if there exists a sequence of real numbers whose range is S. So if we have the following set S, which with elements, then S is countable. If we have a sequence, so we have these real numbers 1, 2, and so on. So there exists a function which takes these real numbers and gives us back this element. Basically, if we can label S, then it's countable. It's easy to see that first, finite sets are countable. Natural numbers and integers are countable. The rational numbers are itself countable. But any interval, it doesn't matter, closed, open, or semi-closed, is not countable. And by convention we say that empty set is countable. Now let's talk about the convergence. When we were studying the elementary calculus, we know that the following sequence is getting closer and closer to 0. What we want to do is formally define the idea of getting closer. A sequence of real numbers is said to converge to some real number A if and only if for all epsilon greater than 0 there exists some big N in natural numbers such that for all n greater than equal n we have that the distance of the sequence and this limit A is less than epsilon. Basically what we are saying is that give me some epsilon, then my job is to find big N such that after that N the distance is getting closer and closer to 0. The following phrases have the same meaning. Xn converges to A, or A is a limit of Xn, or Xn goes to A as n goes to infinity. The way you can understand the convergence is think about that the sequence Xn goes to A as n goes to infinity. Then A, what we are trying to do, we are thinking Xn as a sequence of approximations to A, and epsilon is a upper bound for our error, and we want to choose n such that this epsilon is getting smaller and smaller when we increase n. Let's visualize it. So if this is our real line, this is the point A, and those are the boundaries A minus epsilon, A plus epsilon. Then if this is our sequence, and if it's converge, what we are going to see is that after a while we'll have cluster around A. Now let's do a couple of examples. So the first, what we want to prove is that 1 over n goes to 0 as n goes to infinity. Intuitively, you may find that this is true, as if let's say n is 100,000, then when we divide 1 to over 100,000 we get number close to 0. But we need to mathematically give a proof of this. To prove it, we use the definition of the convergence. Now, you give me some epsilon greater than 0, and my job is to find n such that after that the sequence is getting closer and closer to 0. Now, what if I take n as a floor function of 2 over epsilon? Now, for all n greater than equal n, it is true that 1 over n is less than equal 1 over big N. So from here, now let's use the definition. We have that 1 over big N minus 0 is less than equal epsilon over half, which is less than epsilon. And based on the definition of convergence, we prove that 1 over n sequence goes to 0. To make you comfortable with proving things, I will illustrate the proof of one more lemma, which says that a sequence have at most one limit. So our options are sequence may not converge, or if it's converged, the limit is unique. The proof is by contradiction. We say that by contradiction, sequence does not have one limit. It means there are one and more, let's do two, without loss of generality. And we say suppose xn converges to A and xn converges to B as n goes to infinity. From here, by definition of convergence, we know that there exists some n1 and n2 such that for all n greater than n1, we have that the sequence is getting closer and closer. So epsilon over half, we took epsilon over half to make things easier, since you will see at the end we are going to sum two parts and we need epsilon half to make the proof more representable. And the same way we know that for all n greater than n2 we have xn minus b is less than epsilon half. So from here, if we take n as a maximum of n1 and n2, we know that for all n greater than equal n less than epsilon 2 and xn minus b is less than epsilon 2. So from here we can use triangle inequality and write a minus b as a minus xn plus b minus xn. So this is less than equal epsilon half plus epsilon half, not equal, strictly less, which is equal epsilon. So we have that a minus b is less than epsilon and epsilon is arbitrary. But does this mean that a should be equal b from here? So what we get is that a and b are arbitrarily close to each other, so very close. We can use the definition of absolute value and end up that a is less than equal, a is strictly less than epsilon plus b. From here, a less than equal b. The same way, b is less than epsilon plus a, so we have b is less than a, and from here a equal b. But this is contradiction, since we say that a and b are not the same point, and the lemma is proved. Sequence can be bounded or unbounded. We say that the sequence is bounded above if there exists some real number m such that for all n in natural numbers xn is less than equal m. So the same way we can define what we mean by bounded below. The good question is there any relation between convergence and bounded? Now we will prove that every convergent sequence is bounded, but vice versa is not true. To see this, why bounded sequences are not always convergent, let's do example. Suppose we have the following sequence. So the members of this sequence are minus 1 1, minus 1 1, and etc. Definitely this is bounded. The upper bound is 1 and lower bound is minus 1, but this sequence doesn't converge, since whatever point you take, the difference can't be less than epsilon, since if limit is minus 1, then 1 minus 1 is 2, so it doesn't converge. Now let's prove the following theorem, which says that every convergent sequence is bounded. To prove this, let's take epsilon greater than 1. Since the sequence converge, then we know that there exist n in natural numbers such that for all n greater than equal n, the difference of the sequence and the limit is less than equal 1. From triangular inequality, we can get that the absolute of xn is less than equal 1 plus absolute a. Now we get that for all n greater than equal n, the sequence is bounded. The next question is, what about the sequence before n? So to see this, we have the following. This is our sequence x1, x2, and etc. We have some n. After that, this n getting absolute closer to a, and we found that after this period the sequence is bounded. Now we are interested on this part. We can write that for all 1n, we have that less than equal n, where this is maximum of x1, x2, xn, and etc. Therefore, our sequence xn is bounded by maximum of m and 1 plus absolute value of a. Next, we will learn two important theorems which we use this theorem to prove that sequence converges. Theorems have the name which called the squeeze theorem. Why squeeze, you will see a little bit later. So if we have the three sequences xn, yn, and wn, the squeeze theorem says if xn goes to a and yn goes to a, then we can find some n0 in natural numbers such that if this holds, so if each element of the sequence is between xn and ym, where n and m are different, then wn should be goes to a as n goes to infinity. To see this, we have two sequences, xn and ym. So this sequence goes to a, and ym also goes to a. But also we have the third sequence wn, which is always between these two. So the intuition is there is no way that wn can go except to a. That's why it's called squeeze theorem, since wn is squeezed from the left and from the right. The next theorem says if x is a limit of sequence of xn, then if a is between a and b, then we have that the limit also should be a and b. There are cases when we want to adjust sequence or correct sequence to make it convergence or make it converge faster. To do this, we need something which called subsequence. A subsequence of the sequence xn is a sequence of the form x nk, where nk is the natural numbers and n1, n2, and so on. That is, we get the subsequence xn1, xn2, etc. by deleting some terms of the original sequence xn. For example, if we are dealing with the following sequence, then we can find the subsequence of only once if we take that nk is equal to k. By doing this, you see that we make the subsequence converge to 1, but the original sequence does not converge. We say that if a subsequence converge, then the limit called a limit point. As of this point, the interesting thing you may notice is that although the sequence does not converge, however, it has convergent subsequence. This is not a coincidence, and what we will see that every bounded sequence has a convergent subsequence. But before going there, let's start defining monotone sequences. Let we have a sequence xn of real numbers. Xn is increasing if and only if x1 is less than equal x2 and etc. The same way we can define what we mean by decreasing or strictly decreasing, and we say that xn is monotone if and only if it's either increasing or decreasing. Now we define the theorem which showed that every convergent sequence is bounded. So if we have the xn which is monotone and bounded, then it converges. In other words, the sequence xn has a finite limit. But we do not prove this since the proof is a little bit involved and out of the scope of this lecture notes. Let's do instead the example. If we have that I greater than 0, then and the second example, if we have that absolute of a less than 1, then an goes to 0 as n goes to infinity. I will show the proof only of the second part. The first thing you may notice here that to prove this, it is suffices to prove that an is convergent. So the absolute value of a to n is convergent as n goes to infinity. So to see this, you can use Squeeze theorem to show that why it suffices to prove this only for this absolute value of n. The thing is, absolute value of n is monotone decreasing. Since a is less than 1, and we know that if the number is less than 1, then if the power n plus 1 power is less than n power, and absolute of n is bounded below. This is by definition of the absolute function, that it cannot be below 0. It cannot be negative. Then we can use the theorem above. Then from theorem, let's write above, but usually you need to give some name to it. Then from theorem above, we know that the limit exists. The next thing we want to prove is that in addition, L is equal 0. Suppose by contradiction not. L is not equal 0. Then, since we can write absolute n plus 1 power of absolute A as absolute A times an, and if we take the limit from both sides, from the left and from the right, we get that L is equal absolute value times L, since the power of n plus 1 goes to A, and this one is also goes to L. However, since L is not 0, we get that absolute value of A is 1. But this is contradiction, that absolute value of A less than 1. So we have this in the way we define A. So this is contradiction, and we prove that L should be 0. So the limit should be 0. In the future, we may have the situations when we want to deal with the generalization of limits. We define if we have the sequence xn, then the limit c prime of xn defined as limit of the supremum of xk such that k is greater than n. And the same way, limit of infimum of xn is defined as the limit of infimum xk such that k is greater than equal n. Now let's understand what's the idea behind this. If we define the sequence Sn as the supremum of xk, let's start by saying, suppose this is our sequence x1, xn, and so on. How we construct the new sequence Sn? We each time take one x out. So this is our x. So the first, so this is our S1. Our S2 would be this supremum of without x1. What happens when each time we get rid of our left element, and the supremum of whatever remains, in our case S2, should be less or equal to the previous S1. That means that the sequence Sn is decreasing. Thus, if as well xn is bounded, then by definition, by the theorem that we mentioned a couple of slides ago, the limit exists. That's the whole idea of lim supremum. The same way we can define what we mean by lim infimum. To see lim infimum, what we do for lim infimum, if we have the sequence x1, xn, again, each time we get rid of one element from the left, but in this case, what happens with the infimum, when we take one element out, the sequence is infimum of the sequence is getting bigger. So if we define new sequence L1, Ln, then this sequence is increasing. And then if xk is bounded, then we can, again using the same theorem, that the limit exists, and that's the whole meaning of limits, lim. Now let's do one example. We want to find limit of supremum and limits infimum of the set of, let's say, -1 to n. You see that this is a set of -1, 1, -1, 1. This is the following sequence. If each time we get rid of something on the left, infimum and supremum of the sequence does not change. Thus, lim inf is -1 and lim supremum is 1.